Hello everyone, and in this class we're going to look at digital image processing. We're going to learn on how we can be able to perform spatial filtering. In that case, that is what our objective for this class today. So I believe by the end of today's class, you'll be able to understand what is spatial filtering. In that case, be able to have a good interpretation of how these concepts can be able to help us to become good machine learning engineers, good data scientists, and good at our different places of work. Now, we're going to look at the fundamentals of spatial filtering. Now, before we get to that, let us first of all understand what is filtering. Now, filtering is the process by which we can able to accept or reject certain frequency components. Now, these frequency components that we accept or reject have an impact on our image. And the result of that is that they can effectively smoothen or they can sharpen image. Now, this is useful because this application or the results that are obtained thereafter can be used for image restoration. Now, you might be asking yourself, what is image restoration? Image restoration is nothing but the process of restoring an old image and removing noise and other disturbances in the image through filtering so that you can be able to get a high quality image. A good example is how you can be able to convert an 1918 image and be able to see it in colored form as well as with detail that can be able to be performed through image restoration. Now, we have different types of filters. The first filter we have is the low pass. The second filter that we have is known as the high pass filter, and we also have a spatial filter. Additionally, we have much more filters that we'll be looking at in the subsequent classes. Now, when we apply filtering operations on an image, we can be able to use a spatial domain. When we use a spatial domain, it means that we are trying to filter this image using different filters. And in spatial domain or spatial filtering, we have several types of filters which are known as, we have different methods. The first method is known as the kernel method. The second one is the spatial mask. The third one is the template, and the last one is sliding. The reason why we have these several filters is because they are very useful in both linear and non-linear filtering operations. Now, moving forward, we have two types of spatial filters. The first one is known as a pixel-to-pixel, or commonly known as point-to-point operation, and the second one is a neighborhood, which is also known as mask-based operation. Now, when we talk about neighborhood operations, we have so many things that come into mind. Two operations come into mind. The one is known as operation with n by n filter, which is also known as the order statistic filter. These include the mean, max, and the minimum. The second operation that we have, also known as the correlation or the convolution. Correlation means that you are trying to look for relationship that exists between different data items. For example, if we are trying to identify how is one region of an image, the features present in one region of an image similar to other region of an image. In that case, that is known as correlation. Then the other fundamental aspect of spatial filtering is the linear and nonlinear filter. Now, this operation is very similar and it is very necessary whenever we are using image pixels that are not linear, or sometimes they refer to as nonlinear. Now, having mentioned on the types of neighborhood pixel, then neighborhood filters, where we mentioned we have n by n filters, or sometimes they are known as order statistics. Now let us understand clearly. Now, order statistics filter are basically filters that are non-linear in nature. Non-linear to mean that they are used for non-linear pixels. How do they affect an image? They affect based on order. Order means they can be able to be applied to, they are applied to an image, and they can be able to increase or decrease the pixel of an image that is surrounded within a given region. This region is known as a neighborhood or a mask. So we can be able to apply a sliding technique to this pixel in the form of a filtering algorithm. So this sliding window can be applied to a filter algorithm, and in that nature we can be able to increase or decrease the pixels that are present within that region. Now, this is what occurs. Whenever we apply this sliding window, I want you to keep in mind the example of sliding windows we have in the office. These sliding windows, we can either be able to move them to the right or left within a given perimeter region. Now, whenever we perform this sliding window on an image, we replace the value of the center pixel with middle value that is determined by the ranking. I repeat, suppose we have a 3 by 3 matrix. So that means we have 3 pixels on the vertical direction and we have 3 pixels on the horizontal direction. In that 3 by 3, we have a middle pixel. So we replace this middle pixel by the value that is obtained by a ranking result. This ranking result is obtained using the order statistic filter, which is either median, max, or mean. Now let us look at the median filter. Now the best result for showing salt and pepper noise is through median filter. Salt and pepper noise is basically black and white noise. Okay, so these salt and pepper noise provide excellent noise reduction without the provision of smoothing effect that can occur whenever we are applying this smoothing. This is an example in which you are going to look at how we can be able to perform a median. Now, in this image, we have a pseudo image. This pseudo image, we are trying to show how we can be able to apply a high frequency of value 10 and 50. 10 to mean that 10 is the maximum value at a given matrix mask, and 50 the central value. So what occurs here is that we are trying to replace the value at the center, which is 50, with the maximum value that will be obtained from this filter mask. Now we remove using the 3 by 3 median size filter. That means when you obtain the value 10, you're going to perform a median. So median is a statistical technique where we first perform mean, then from the mean we find the square root of the mean to obtain the median. Or that means that is the variance. So to repeat the same, median is the middle value within a given set of values. So for example, if we are going to apply this mask of 10 by 10, the middle value is 10 here. That is labeled with red. This value is what you are going to store. Then after storing that value, we move to the next step where we'll now view the next value. So as we are moving to this direction, we are sliding. So initially we were at this point, now we are at this next point. So here the maximum value that we have is 50. But since we are interested in the median value, collect 10 as our median. Next, we will move towards the other direction. We We'll also monitor which is the maximum value, and the maximum value we have is 10. Then the next value that you're going to look at is the value that you have here. So here we have the maximum value to be 50 as well as 10. But remember, we are collecting the median value. So we'll not retain 50, but instead we retain 10. Now, since we have 50, we will move towards the direction where we have 50. So in this case, we will have 50 as our maximum value. And when we look at the median, we see the median value to be 50. So our direction will now move towards where we have. So we have come to the middle value where we had our middle value. So the middle value for this image was 50. In this case, this sliding window, we have our median value as 50. So what happens in that previous image is that we will now retain this 50, and now we will not replace any value because our median value was 50, and that value sent the middle value of this neighborhood of n by n, 8 by 8 was 50. So that 50 will be changed. So that is how we calculate the median. Next, we are going to look at the max filter, and the max filter is one of the order statistics that you can be able to apply to an image. So by so doing, we'll be able to understand how we can be able to enhance our image in terms of quality. So let us look at it. So max filter is basically used to find the brightest point in an image. Now, when we have a digital image, this digital image can have two sections. It can have brighter points as well as darker points. Now, when we want to find the brighter points, we use the max filter. So how do we do it? We select the value, the largest value within the pixel values. So the response of a 3 by 3 matrix filter is given by R, the response, which is now given by the maximum value within that filter, and that is obtained by Z of K, where Z is a function which is equal to any number within 1 to 9. 1 to 9 to mean this 3 by 3 filter will have points, will have 9 points. Okay, so those 9 points will be having different brighter, will having different pixel values. So for example, if the value of K is 1, so that means that is the first pixel. So the first pixel can have the value of 255. The second value of K, which is 2, that is the second pixel, can have the value of 144. So we'll pick the maximum, the points that have maximum, that have maximum pixel, and that maximum pixel now correspond to the size. So if we have a 16 max filter, the value of K will be equal to 1 to 16. If we have 32, we'll be having 1 to 32. But now the value of the pixel, the pixel range is between 0 to 255, we'll be having different variations of values from the range of 0 to 255. Next, we have the mean filter. The mean filter is used to find darkest point in the image. So it selects the smallest value within the pixel, and that is denoted by the response mean Z of K, where K is now the size of the filter. Okay. The same case here, instead of picking the maximum value, we pick the smallest values. Now, the next step that you're going to look at is on the following, which is now the sharpening spatial filter. Now, the principal objective of sharpening is basically to highlight transitions in intensity. What we are focused on is to highlight the intensity. This means that we want to improve the quality of the image. So so that we don't get blurred regions. Instead, we get very visible and sharper edges, and that can only be able to obtain by performing a spatial filter. Okay. So one application in which you can be able to perform this on electronics printing, medical imaging, as well as industrial inspection, automobile guidance in militaries. How is that possible? Let us look at all of these applications one by one. In electronic printing, this is possible especially when we want to print billboards and banners. So when we do so, it means that we have to get very detailed images that can be able to be visible by the public. So in that case, we require to perform spatial filtering in case the image is distorted. Medical imaging like MRIs, scan, X-ray, they require us to have very detailed images so that they can be able to help the surgeons perform proper medical diagnosis. Industrial inspection, for example, whenever we want to look at in an engine that has knocked, we need to see which components are not working properly. So for that case, we need to find a fault in the engine, and in that case, we require to have maybe a 3D scan of the image so that you can be able to see the internal components without necessarily opening the engine. That way, you can be able to troubleshoot the engine and be able to get where we need to repair. Autonomous guidance in military systems, especially where we have robots that are being sent to regions that are very hostile for human habitation. That is very necessary so that the robot can send very crystal clear images. So these crystal clear images will help the military to be able to encounter the enemy and also to retaliate when the right move. So the one thing to remember is we have something else that is known as a derivative. What is a derivative? Derivative is basically a different digital functions that is defined in terms of differences. Now, in your mathematics, first year and second year, you studied on integration and differentiation. That is where now this is applied. Now, let us look at the first derivative. For the first derivative, we have conditions, and these are the conditions. So the conditions to be applied are as follows. So in the first step, must be 0 in areas of constant intensity. Constant means there is no change. It is fixed. So in that 0, the difference, remember here the derivative is in terms of difference. So the difference between one region of intensity and the other region of intensity is 0. The difference is 0. Also, it must be non-zero on the onset of intensity of steep and slope. So for those regions, the difference between a steep regions of steepness must be non-zero. That means they have to be any value that is greater than 0. That is 1, 2, 3, and n, where n is not 0. Similarly, whenever we are climbing or where there is a ramp, then that has to be non-zero. So that also has to be not 0. So for first order derivative of a one-dimensional function, so one-dimensional function means one axis, either f of x or f of y, is a difference of, so the difference is given by f over x, which is given by f plus 1 minus f of x. This plus 1 is the difference that is obtained either by a zero region of constant or a region of intensity. Then we have the second order derivative. So the second order derivative, it must be zero in the constant areas. Also, it has to be non-zero in regions where there is a ramp or a steepness. It has to be zero along ramps of slope constant. Okay. Now, whenever we perform this second order derivative, this is the equation that is used. So f into x plus 1 plus f into x minus 1 minus 2 into f of x. This is a diagrammatic illustration of the first and second order derivative. Now we have the diagram here that is going to help us so that we can be able to understand what exactly occurs whenever we are talking about intensity ramp constant. Now you can see in this first diagram, we first have the scan line of x. X here to refer to the x-axis. Okay. Then the next thing that we have is the intensity. So as the intensity shifts, so we have 0, 1, 2, 3, 4, up to 6. Now we want to see how this first order derivative can be obtained in the changes in intensity. Now we've said when these points of intensity are going to be recorded on a scan line, and from this scan line, we are going to perform the first order derivative using the first order equation. Now this occurs the following way. So we have the constant intensity where we are having 6. So we will record them as 6. Now, to be able to perform this first order derivative, we will now be able to now find f of x, which is now 6, plus 1, which is 7. Then f of x minus 1, that is 6 plus 1, going to be 5. So here we'll have 6 plus 5 is going to be 11. Now 11 minus f of x. F of x was given by 6. 6 into f is going to be 12. In that case, 6 minus 12 minus 1 minus 11 is going to give us 1. Now that is exactly what we have here. So that 11 minus 12 is going to give us negative 1. That is what is stored here. Now, the ramp, similarly, we are going to now start from negative 6 to 1. So you can see it's non-zero. And similarly, here we have constant, the value is 1. We are having a steep, the values are changing from 1 to 6. So it is non-zero. The difference of this first order derivative is going to be 0, negative 1, 0, 5, and 0 respectively. For the second order derivative, first step it has to be non-zero, where we're having a slope, and a 0 where we are having a constant, and non-zero where we are having a steep. So the same thing occurs here. This is the product. This is the difference of the equation, differentiation equation. Next thing that you're going to look at is known as the Laplacian. Laplacian is basically the combination of the differentiation derived. Actually, in simplest form, Laplacian is the combination of the second derivative in both x-axis and y-axis. So when we combine both the differentiation of second order derivative in the x-axis and we add the sum in the y-axis, we get the Laplacian. And this is the equation. Since we are using the x and y axis, that is why we say the Laplacian is a linear operator. Excuse me. Now, the next step that you look at is the discrete form, how we can be able to change this equation in the discrete nature. So this is what occurs. We have f of x into x plus 1 comma y, because we said in Laplacian we are taking account of both the x and y axis, plus f of x minus y comma y minus 2 into x comma y. Now, if you look at this equation, what is happening here is that we have just added the y axis on the second order derivative. So the same thing will occur here. So we'll first have the x, and then we'll add x plus 1, then plus f into x comma y minus 1 minus 2 into f into x comma y. So all these, we can decompose them together into one equation and say that change of f into x comma y is given by f into x plus y comma 1 comma y plus f into x comma y plus minus 1 comma y plus f into x comma y plus 1, etc. So the product that we get is just the combination of this first x direction plus y direction. The next, so this filter to implement Laplacian. So what occurs is that these regions of interest, now pick them and we'll now be able to substitute them to the Laplacian equation. So having said that, let us look at these questions. The first question is, if h into rk given is equal to nk, where nk is the kth gray level and nk is the total pixel with gray level rk. So rk is a histogram in a gray level range 0, L minus 1. Now, how can we normalize a histogram? So we are looking at histogram normalization. One thing to remember is whenever we are performing histogram normalization or histogram equalization, is that we take account every value of the histogram, and those values we have to divide them from the total number of pixels in the image. So by doing so, we can be able to obtain our equalized histogram. Having said that, let us look at the options and see if we have anything that is closer to that. The first option is if each value of histogram is added to the total number of pixels. So here we are not performing addition, we are doing subtraction. Second option is if each value of histogram is subtracted by total number of pixels, image say n into n comma p into rk equal to nk minus n. Here is not true because the subtraction is. So the third option is if n value of histogram is multiplied by total number of pixels in image, say n. So p into rk given by nk into n. Here similarly we are doing a multiplication, so hence the output is not true. So if the value of histogram is divided by total number of pixels, say in image, say p n comma p into rk equals to nk divided by n, correct? The main essence is division of total number of pixels by the value of, so our result is. Next question. Using gray level transformation, the basic function linearity deals with which of the following transformation? And in the previous class, we looked at 3 types of transformation functions. First one was the linear function. second one was the logarithmic function, and the third one was the power law transformation. So in this case, under the linear, we looked at the identity as well as the negative transformation. Under the power law, we looked at the nth and the nth root transformation. Under the log transformation, we looked logarithmic, we looked at the log transformation and the inverse log. Now, having said that, answer is B, where linear function deals with negative and identity transformation. Which of the following operations is or are equivalent to negative transformation? Negative transformation means we are doing a subtraction. So in that case, we are looking for a result that will give us a negative, and means addition, or means, and means multiplication, or means addition, not means subtraction. Therefore, our result is we are looking for a negative operation, and that is C, which means. Next question is, which gray level transformation increases dynamic range of gray level image? Dynamic range occurs whenever we are trying to look for a region of interest whenever we are performing a contrast stretching. Whenever we perform a contrast stretching, we can increase the intensity value, the regions that we have desired. The opposite of contrast stretching is thresholding. In thresholding, we are only interested in fixed regions of black and white. Hence, for that matter, whenever we want to look for dynamic range of gray level transformation, we perform the contrast stretching. So power law is not possible, and negative transformation is not our output. So our answer is a specific range of gray level highlighting the basic idea of. Now, contrast stretching, we are dealing with dynamic range. Bit plane slicing, we are dealing with only bit level information. Thresholding, we are dealing with only intensity values that involve regions of black and white gray level patches. However, when we deal with now gray level slicing, we are highlighting gray levels within a specific range. Hence, our answer is gray level slicing. Next question is, what is accepting or rejecting certain frequency components called as? That is what we have covered in today's slide. That is what we covered in slide number 2. Said filtering is the process of accepting or rejecting components of an image that is known as filtering. Said filtering can include both enhancing the image by increasing or reducing the pixels, and if we do so, we can enhance the image, and one application is image restoration. So our answer is A. Which of the following filter has the response in which the central pixel value is replaced by value defined by ranking the order in the pixel encompassed filter? That is what we've looked today. We've looked at order statistics filter. That means we looked at the median, where we said we replace the middle value with the median value. We mentioned on the mean, where we take the darkest point and we take the response of the minimum filter for a mid filter. Max filter, we take the brightest points for the maximum values. So for non-linear spatial filter, that is exactly what we're looking at in terms of spatial filtering. Hence, our answer is Next question is it true or false that the origin pixel value is included while computing the median using gray level in the neighborhood of the original pixel in median filter case? Median filter, we use the original pixel value, and that original pixel value is what we use to be able to replace it with other median values obtained from the mask of the median. Next question is, which filter used to find the brightest point in the image? The filter that is used to find the brightest point in an image is the max filter. The filter that is used to find the darkest point in an image is known as the min filter. Hence our answer is. Next question is, which of the following is or are a non-linear operation? So non-linear operation can include computation of variance so that you can obtain the median, computation of median so that you can just directly obtain the median value. So all these mentioned techniques are basically useful for nonlinear operations. That is what we have covered today. So to recap on what we have discussed today, I'll go to the first slide. Define what is filtering, and the quiz you've seen that. Filtering is image restoration. Such examples of filters are low pass, high pass, and in spatial filters we have different methods such as kernels, spatial mask, templates, and sliding windows. So spatial filters are useful because they can be used for both linear and non-linear functions. So we talked of the different types of filters, and we said the different types of filters include the point-to-point operation, have the mask or the neighborhood operation that can apply the min, max, and minimum. Okay. Another mask-based operation is correlation, where we compare values from different filters and we get the desired filter that we talked about different order statistics. So in order statistics, we employ increasing or decreasing the pixels so that we can be able to achieve the desired results. By so doing, we can apply the sliding window, the templates, we can be able to use the other filter techniques that we have mentioned. So in that case, we can be able to apply the min, median, and max. So for the median filter, we can be able to provide the best results by removing salt and pepper. This is very useful for the reduction without technique. So this is an illustration of the order statistic filter that you use, where we apply the sliding window to obtain the median value. Next, we have the max filter. The max filter is used for obtaining the brightest points. We use the response R to obtain the max value, and Z the size of the filter. So for example, 3 by 3 will give us 9. So for that case, we have to mention 1, 2, 3, 4, 5 up to 9, so that 1, the pixel value of 1 is 255, and that is the maximum. It will be represented by Z. Similarly, for minimum filter, we take the darkest points, and in that case, we are able to show the minimum points. The formula R equals to min bracket Z of K, K 1 to 9. So in this case, we can apply the first derivative. So the first derivative, we can use the value 0, non-zero for slope, non-zero again for ramp. This is the equation in the x-axis, in the axis. The second derivative, just combine the values for both the slope as well as the ramp. This is the illustration of both the first derivative and second derivative as mentioned before. And this is now the output of the Laplacian. Laplacian is basically the combination of both the first, second derivative in the x-axis, the y-axis. So when you combine both of them, you will obtain the results. I repeat again, in the Laplacian, we take account of this equation. This equation is showing in the x-axis, f of x. So when we find another one for f of y, and we combine both, that is what is known as Laplacian. So basically, it's just a second derivative both x and y axis. That is what here. So change of square f is given by f to the image, that is the image function in the x-axis and the image function in the y-axis. Since we are using the x and y axis, this is known as a linear operator. To express this equation in the x direction, this is how we perform it. So this is just the second derivative equation, the x-axis, second derivative equation in the y-axis. You can have a look again. This is the second derivative equation in the x-axis, which is definitely shown here, and in the y-axis, shown here. Okay. So the difference that occurs is that we add y. So we just mentioned both f, x, and y, f of x plus, comma, y plus 1. Now, when you this thus discrete Laplacian of two variables is the variable of x and y axis can now be represented by this equation. That was it, and now we can be able now to present all of them this equation. Okay. So you can see the central value here is -4 for the x-axis, +4 the axis, -8 the negative axis, +8 the positive axis. So this is the result that you obtain whenever we are performing this equation. So students, we have come to the end of today's lecture, and I believe that whatever we have covered today has been beneficial to you, and now you can be able to use it and apply it in the next class that we'll be studying. So if you've not been able to follow up with what we've covered in today's class, I request you to go back to the first two lectures that we have shared with you. So you just go through them. The first one is Introduction to Digital Image Processing, where we define what is an image, what is the component of an image, how is an image formed. Now we talked of the next class where we talk of the spatial filters, and now today we've looked at the different order statistics filters in the spatial filtering domain. So we have two types of domain, that is the spatial domain and the frequency domain. So all this that we are covering is basically the spatial domain. After this spatial domain, we'll be looking at the frequency domain in the subsequent lectures. So thank you for your time. Let's meet again in the next